Welcome to the course on storage technologies. My name is Fokko Mulder and I work at the Faculty of Applied Sciences of Delft University of Technology on energy storage and conversion technologies. This module is divided into 5 videos where we will learn about the following topics. Know the role of storage in a renewable energy society. Understand timescale of energy storage technologies. Introduction to storage solutions and typical energy densities, efficiencies and cost, drivers for energy conversion, and you can reflect on the energy efficiency of intermediate storage. Today we make a start on the first driver for energy storage, which is the generation of renewable energies. The learning outcomes of today are renewable energy generation potentials, the characteristics of generation methods. Renewables generate mostly electrons, but we also need molecules. That's what we will learn about. And intermittency that requires storage. Energy storage is related to energy supply and demand mismatches. Today we first look into energy supply. Our energy supply in the past we had mostly fossil energy, as you know, but since about a decade, the wind power and solar power starts to take off. You can see that on the graph here. Before that, biomass and hydropower were already available on significant scales. But what will the future bring? It will go towards more and more renewable energy use. And that's because of the Paris Agreement in 2015, where the target has become to reduce carbon dioxide emissions by 80 to 95%. So the use of renewable energy has to speed up by 2050, ultimately going to a fully renewable energy-powered society. In order to arrive at a fully renewable energy-based society, we have to look at which renewable sources are available, based on their technical potentials, as you see in this graph. In this graph of the IPCC, one can see the most prominent options. As you will see, solar power has the largest technical potential of many thousands of exajoules per year. That is much more than our current world energy use. Another important one is wind power. A common factor of both solar and wind power is that they generate electricity that is different than biomass, which is also in the graph, which generates materials, so molecules. As you see here, there is a significant difference in the range of estimations in this graph, which is indicated by the higher and lower values of these rectangular shapes. As solar and wind power are reaching the terawatt scale already, these are the largest installed capacities by now, and they are already starting to realize their technical potentials. Therefore, we mostly look into those technologies that both generate electricity directly. Biomass is different in the sense that it generates materials and fuels like biodiesel, ethanol, or biogas. So it appears that the most abundant renewable energies will be solar power and wind power as a good second. Biomass is facing quite some uncertainties in relation to its availability at low enough carbon dioxide emission levels and also in relation to the competition with food production. Looking at solar power, the graph shows the seasonal dependence of the peak in solar light during the year. And that is at 12 o'clock local time and with a clear sky on these different latitudes that are indicated. There is a large difference between summer and winter, as you can see. Also, wind power has systematic intermittency, and that is because wind is driven by thermal effects of air heating up the earth, and that's heated up by the sun. And the graph shows average wind speeds over a large area in the US, often there you see an average that there is more power available during the day than in the night. Note that the wind power scales with the wind velocity to the third power. On top of that, wind also has a seasonal effect to it. More wind energy is available in winter than in summer. Another source of energy is biomass. This delivers materials and molecules, as stated before. The amounts per square meter go up to about half a liter of bioethanol for switchgrass and poplar trees. That corresponds to about 5 kilowatt-hour per square meter per year, and it's a good indication of what you could harvest. And such energy yield is not that much when you compare it to the other sources, the solar power, for instance, which could reach 200 kilowatt-hours per square meter per year, which is quite a bit more. However, it are molecules that can be stored and also used for chemical feedstock. And that's something we also need. The current electricity use is indicated at the bottom by this wavy blue curve. It is shown for 1 day, so 24 hours, in each of the indicated months. And if you look to the total energy use, it's much larger, however, and it looks like this on these 12 days throughout the year. So this wavy gray curve and now blue curve. If one needs to generate enough energy in a renewable way, using mostly solar power, because this has the highest yield per surface area, and also a little bit of smaller amount of wind power, together it looks like this green curves on these days. So that's a very average look at it. Note the very day and night and seasonal dependent generation of solar and wind power together. And note that in order to harvest enough energy, there needs to be a large overshoot of energy generation compared to the instantaneous use. And that is just to get enough harvest of energy throughout the year. And it's also nice to indicate the International Energy Agency's phases for making use of renewable energy. So what did we see? There will be an amount of energy generation. Where? That's the question. And how? And when? Also energy use is there, in what form and when? And then in the previous slide, we saw that there is a big mismatch, but when does it happen? And as a result of all these factors, we finally can expect that energy storage is required to get to a functioning energy system. From the way the mismatch appears, it is clear that one requires storage on 2 typical timescales. Day and night mismatches call for short-term storage on the scale of multiple hours. There's also a seasonal mismatch coming from high solar supply, mostly in summer, and less in winter, and that calls for long-term seasonal storage. So that's it for now. Thank you.